So we are continuing with our class EC469 Opto-Electronic devices. We are looking at module number 1. And this is our 7th lecture. So in this class, we are going to look at the first and important one is quantum confined Stark effect. Then we look at deep level transitions. And last, we will look at Auger recombination or Auger process. So before coming into quantum confined Stark effect, let's see what a quantum well is. Okay, a quantum well is very important since it is used in LEDs, lasers, and even in some optical modulators. Because you can control the efficiency and the spectra or the spectrum of a radiation using the quantum well. So let's see what the quantum well is. So as you know that you have a conduction band and a valence band. Okay. So let me draw it a bit more in width. Fine. So if an electron will be in some energy state in the conduction band, which will be freely roaming in this energy state. So at any position in this energy state, electron have that constant energy. Now at some point of time, while it is roaming in this energy state, it will fall into something called as a quantum well. So the electron will fall into the well called as quantum well. This in a similar situation, if we are taking the case of a hole, then it will go up in the energy table and it will occupy an energy state higher than that of the valence band energy state, and that is somewhere here. So this well in which electron is falling is called as a quantum well. So this has only one quantum well, what I have drawn, and we will see a situation in which you have multiple quantum wells. Now how is this well created? So let's take an example. Let's take an example of indium, gallium, arsenide. Okay. So the gallium arsenide itself is a semiconductor, and indium is another material. So there is a separate band gap for gallium arsenide and indium. So when you combine this using a heterojunction semiconductor, okay, so then you have an energy state for conduction band and valence band produced by indium, and there is another energy states which is produced by gallium arsenide. And for gallium arsenide, the band gap is less. Okay. So, when you draw the corresponding band diagram, you see that the gallium arsenide will produce something called as the quantum well. So, quantum well is a property of a heterojunction semiconductor. Another example for quantum well is example silicon germanium, where germanium will produce the quantum well. And the quantum well doesn't mean that our quantum well has energy states within itself. So, there can be one energy state here, another energy state here, another energy state here, etc., etc. So, there is an energy E1 here, E2 here, and can move up. So, electron can occupy any one of the energy state inside the quantum well. And as we say always, these energy states are quantized, means electron can occupy only a fixed number of energy state. Now, why it is called as a well? So, once electron falls into the well, then to come out of the well, the electron needs to have a huge amount of energy. So, let us say the potential is V0 here. So, electron needs to have this much amount of energy to go out or to come out of the quantum well, and that is not a small energy. It needs higher energy by some external simulation or by increasing temperature very high. So, an electron is trapped inside the well. Electron is trapped in the well and needs high energy to come out of the well. Now, the explanation here that I have said is with respect to electron, and same thing applies for the holes also. Okay. Now, this I have shown is for a single atom, or you can say single piece of a single part of a semiconductor. Now, the semiconductor have multiple atoms. So, basically the quantum well will expand itself. So, you will have something like this. Similarly, for holes, you will have okay, and for each of the well, the electrons might be trapped. So, there can be electron here or multiple electrons here, electrons here, electrons here, electrons here, and goes. Okay. Now, what is the speciality about this? If you consider an electron somewhere in this conduction band outside the quantum well, the electron can jump from the conduction band to the valence band, emitting an energy h nu as a photon. So, the nu here, so the h nu is because of the E g. Okay. So, if this is E g, So, the corresponding to this band gap you have a corresponding frequency. So, what if an electron from the quantum well jumps to the conduction band, valence band in this band gap? Let us say this band gap is called as Eg well. You see, the Eg well is less than the Eg, means Eg well will produce a new photon of frequency, let us say h nu 0, which is equal to Eg well. So, thus you can have the electron hole recombination gives the electron hole recombination gives distinct set of absorption and emission spectrum. Means you will have different frequencies being emitted from the same material. So, let us say you are considering only the transition from the lower end of conduction band to the higher end of valence band. So, even though there is the frequency emitted from the quantum well and from the normal transition is totally different. So, you will have a different emitted radiation, different frequency emitted radiation. This is the speciality of a quantum well. Now, what is quantum confined Stark effect? So, before explaining that, let me explain something about wave function. Okay. So, wave function is for a particle, for example, electron wave function. The wave function, let us call as Wf, the wave function attempts to describe the total energy of an electron. So, here we are talking about the wave function of an electron only, we are not talking about wave function of any other particle. Okay. So, it tries to describe the total energy of an electron, because for an electron the important parameter is its energy. So, depending on its energy, you can say whether the material is insulator, conductor, whether you have radiative combination, non-radiative combination, etc., etc. And the wave function actually gives the biodata of an electron. So, biodata means you have all the details of any candidate, that is a biodata, name, place, contact details, what you have been, what you have studied, etc. Similarly, all the parameters which defines an electron can be found from the wave function. For example, so you know that electron acts both as particle and wave. So, what is the probable amplitude of electron? That is one wave function. Sorry, that is one part of parameter that you can find from the wave function. It also gives the probability density of finding an electron at a certain position in space. So, usually the wave function is represented by psi, and actually the psi square value gives the probability density of finding an electron at a certain position in space. It also can give you the angular momentum of an electron. Okay. And actually the wave function is used in the Schrodinger equation. So, I am not going into details of Schrodinger equation and how to solve this. Basically, Schrodinger equation gives you the possible energy states using the wave function of a particle. So, this basically gives you the possible energy states of a particle. So, solving the Schrodinger equation gives you the possible energy states of a particle, and the Schrodinger equation uses the wave function to give you the details. So, an example is like an example wave function is something like this. Okay. So, if you look at here, at this point there is a high probability of electron and the tail gives you low probability of electron. Similarly, you can define a wave function for holes also, because holes is also a particle. So, you can have a wave function like this. Okay. And if there is an overlap of electron and hole wave function, for example, here there is a considerable overlap. If you like draw a straight line, you can see that the straight line touches the maximum probabilities of both. Means there is a high possibility of electron hole pair or electron hole recombination. So, an overlap of wave functions for electron and hole implies you have a high probability of recombination. So, I think this details is good enough for us to move forward. Whenever we encounter it again, we will explain it further. So, when you draw the quantum well, let us go back to that quantum well itself. So, single quantum well. Now, in this quantum well, there are energy states. So, in this energy states, you have an electron which has some kind of a wave function like this. And in this energy state at the down, there is a hole, and you have a wave function like this. Let us assume that the band gap is Eg, the band gap in the quantum well is Eg, well, and let us say the energy of the electron is at E0, E, and energy of the hole is at E0, H, and the difference of this energy is Eg, quantum well. Now, you see, if you see the wave functions, you can see both are overlapping or have a straight line connecting the maximums, which means there is a high probability of recombination. And you can also find an expression for or you can relate the different band gaps and electron energies. So, let me just write down the terms. Eg well is the band gap of the quantum well, which is written as Qw. E0, E is the electron subband energy, which means the energy state in which the electron is occupying inside the well. E0, H is the whole subband energy, and Eg, Qw is the, you can define this as emission energy, because when the hole or the electron comes from the conduction band to the valence band inside the quantum well, it will emit an energy equal to Eg, Qw. So, that is called as emission energy, and you can see easily from this as Egw is the sum of Eg well, E0, E and E0, H. So, I can write the expression Eg, Qw is equal to Eg well plus E0, E plus E0, H. Okay. I think now we are ready to define the quantum confined Stark effect. So, the quantum confined Stark effect describes the effect of an external field upon the light absorption. So, it describes basically the effect of an external field upon the light absorption, particularly in a quantum band. So, what happens to this whole structure when you apply an electric field? We saw that in the previous class, when you apply the electric field, the band will tilt. So, will it be the same in the case of a quantum well also? Like, will the band tilts? The answer is yes, because when you apply an electric field to the semiconductor, the complete band, including the quantum well, will tilt. So, I can draw it as like this. Okay, fine. Now, what happens to the wave functions? Will it also tilt? The answer is, the wave function will also tilt like this. So, in the electron, in the conduction band, the wave function completely tilts, like now the maximum is not at the center. Similarly, for the valence band, it will tilt like this. So, if I draw the straight line now, you see that they are not in the same straight line. The maximas never occur in the same straight line, which means the possibility of recombination is less. Or in words, I can say that the electron energy states shifts to lower energies and whole states shifts to higher energies. Means the electron has gone down and the holes has come up in the conduction and valence band respectively. Means the tunneling increases. And the energy difference between electron energy state and whole energy state decreases, because you see that the electron shift to lower energies and holes shift to higher energies. So, the difference in energy will reduce, implies you will have less radiative recombination. Okay. Or in other words, I can say the recombination efficiency reduces. So, if you want to emit a photon, you need to have a sufficient energy for electron to jump to the electron while jumping to the valence band the energy difference should be sufficient enough to generate a photon of energy h nu. Now, the energy has decreased, so the frequency also will decrease. Frequency decreases means it will come out of the normal light or radiation spectra, and this is called as quantum confined Stark effect. Okay. So, this is a very important effect which describes the recombination process under an electric field. Okay. So, make sure you understand that there is an electric field applied. Fine. Let us move on to the next topic, which is deep level transitions. Okay. So, to understand deep level transition, we should understand what is deep level traps. So, when you make a semiconductor, you cannot make it perfect. There will be some kind of imperfections or defects in semiconductor. And these defects will produce an extra energy state in the forbidden gap. So, this defects introduces energy state in the band gap, and if these energy states are close to the energy states are close to the middle of band gap, it is called as deep level trap. So, let us see one example. So, this is your conduction band, this is your valence band, and your middle of the valence band, band gap is somewhere here, assume. Now, because of these defects in the semiconductor and also because of some impurities that you introduce, a new energy level will be formed somewhere near to the band gap. Okay. Now, what is the problem with this? See, if this gap was not there, then the electron might have from the conduction band might have jumped to the valence band, combined with the hole, producing photon. Okay. When you have this extra gap, now the electron will not jump directly to the valence band. Instead, it jumps to the energy state here in the deep level trap. So, this is called as deep level trap. Now, this energy will also be released, but you see now the energy difference that the electron is jumping is small when compared to the previous case when we have a deep level, when we do not have a deep level trap. So, this is small and this is large. So, nu will be high or in the visible region when there is no deep level trap, and whatever energy emitting here, the frequency here, if it emits h nu, this is small, which means that it might not be in the visible region. So, this is basically a non-radiative transition. Okay. So, if there is a deep level trap present, the trap will capture the electron going to the valence band. It will emit an energy which is less than that of the visible light, and it is non-radiative transition. In a similar way, the electron in a deep level can also jump to the valence band. Again, the energy is also small and it will not produce it will not produce a radiative transition. But if you add some impurities, then so if some impurities added, then you can make a deep level trap to give radiative transition. An example of this is adding copper or manganese to gallium arsenide. Okay. So, in this case, you have the band, you added an impurity which creates a deep level trap, and when the electron falls to the deep level, it will emit the photon with energy h nu. So, you can always purposefully make a deep level trap, and this transition into the deep level is called as deep level transition. So, you can define transition is equal to transition to and from the deep levels. Okay. So, we will see everything in different other scenarios when we study the different optoelectronic devices. Okay. And the last part of this lecture is Auger recombination. Auger recombination is important at high temperatures and high doping densities, and it is seen usually at low band gap materials. Okay. So, Auger recombination, or I can say it as Auger process. It is not Auger, it is Auger. So, let us define Auger process. So, Auger process is a three carrier non radiative recombination process in which the excess energy released by the recombination of electron hole pairs is transferred by Coulombic collisions as kinetic energy of a third free carrier. Now, the explanation of Auger process is very big, but let us see what it actually means. Okay. So, let us draw the band diagram. EC and EV. Let us assume that there is an electron here and there is a hole here. Now, the electron will jump from conduction band to valence band combined with the hole. Usually, this will generate energy in the form of a photon or a phonon. But if it is an Auger process, what happens is the energy which is generated by the recombination of electron jumping from conduction to valence band is transferred as a kinetic energy to a third carrier, and it will be moving into a higher energy level, or it will have higher kinetic energy, or it will start moving very fast. This is called as Auger recombination. So, basically in the recombination process only two carriers are taking part, which is one hole and one electron. But in Auger process you have a three carrier participation, where the third carrier will acquire the energy released by this recombination and will move to higher energy state, and it will not emit photons. Okay. So, this electron has kinetic energy transferred from recombination. and this is called as Auger recombination. Now, there are names given for this. For example, this is called as Cchc recombination. C means conduction, H means hole. Cc means 2 electrons. So, this means 2 electrons in conduction band combines with 1 hole in valence band, transferring the energy to an electron in conduction band. So, first 2 Cc means which all are the carriers, the third one is to which it is recombining, and the fourth one is to which the energy is transferred. And this is called as an intrinsic Auger process, because you do not have any impurities. Auger process or Auger recombination. So, if you look at another type of Auger process where you have conduction band, valence band, you have 1 electron in conduction band and a hole in valence band. The electron jumps to the valence band combined with the hole. The energy is transferred to another hole which changes its energy. Okay. So, whatever energy is there, it is transferred to this hole. So, in this case, whatever energy is in this electron is transferred to this electron and moves to another energy state, and this is called as Cchs, where S is called as a split band. Okay. So, these two are basically intrinsic Auger process. So, if you look at an extrinsic Auger process, it can be in a p-type or an n-type semiconductor, where you have an energy level in between the band gap. So, here you can have a electron here and a hole here. The electron jumps from this energy stage to the hole, and it transfers its energy to this electron. The electron goes to the conduction band. Or in another scenario, if the band is here, an electron here and there is a hole here, it jumps to the hole, and an electron in the conduction band receives this energy released by the recombination, and it moves to the high energy level. Or there is one more scenario where the electron from the intermediate energy state goes to the valence band's hole, and the hole in the valence band is getting transferred the energy. This is for p-type, sorry, n-type, and similarly you can have for p-type, where you have a energy level extra at near to the valence band. So, here the hole or the electron jumps to the hole in the intermediate state, and the energy is transferred to the electron in conduction band, and the electron moves up. Or the electron jumps from conduction band to valence band, combines with the hole, and the energy is transferred to the hole in the valence band and goes down. So, these are different scenarios, and this is called as an Auger process. Now, let us see what is actually the physics of this Auger process. Let's draw the EK diagram. So, you have conduction band, you have valence band, y axis is energy, x is k. Now, the valence band can have multiple energy levels. Okay. This is called as heavy hole band and light hole band, etc., etc. So, do not worry about that. So, there is an electron here and a hole here. The electron has a momentum k1 and hole has a momentum k1 dash. There is another electron here which has a momentum k2. So, when the electron, so this is the initial state. So, when the electron jumps from conduction band to the valence band, it gets recombined. This energy is transferred to this electron and it moves to a higher energy level because it gets extra energy. So, finally, you will end up having one electron in the conduction band with a new momentum k2 dash. This is the final version and the momentum should be conserved. That means, this new electron has acquired the momentum of the electron and the hole, or the momentum of the electron has increased tremendously. Okay. So, this momentum is very high. The electron has acquired energy, it has also acquired a high momentum. So, I can state these things as follows. The energy taken by the third particle has energy in the order of Eg and thus have high momentum of the order of root over 2 m Eg, where m is the mass of electron. Because the transition is along the band gap. So, the energy will be in terms of that band gap energy and the momentum will also increase proportionally. So, I can say the momentum cannot be lower than some threshold value, implies there is a lower limit for kinetic energy. Okay. Means the electron will now have high kinetic energy, and because of this kinetic energy, the electron will move along the lattice, it will collide with other charge carriers and it will emit heat. It will gradually collide and subside down, but it will lose its energy by giving heat. So, this the high energy high momentum carrier or particle makes lattice vibrations and collisions giving out heat and loses its energy. So, that has lost its energy by giving out the heat, like it will collide, gives out heat and loses its energy. And as a concluding statement, you can say the rate of Auger process increases with temperature and with decreasing band gap. So, when you increase the temperature, the possibility of that Auger process is very high, and also you can see that from this explanation, if the band gap is very less, then that Auger recombination possibility is very high. Okay. So, in this lecture we have looked at the quantum confined Stark effect, we have looked at quantum wells, and we have looked at deep level transitions, and finally, we have looked at the Auger process. So, this concludes our first module of the course. So, please read through and see the lecture to understand, and let me know if you have any questions. Thank you for listening.